Section 1 Introduction. In the past year, we've seen a significant shift in the world of large language models, LLMs. Models like GPT-4 and Claude have led the way, demonstrating impressive capabilities and versatility. Meanwhile, open-source LLMs like Llama, Falcon, and Mistral have made it easier for researchers and practitioners to use and adapt these models for a variety of purposes. However, there's a growing trend of limiting access to the training, fine-tuning, and evaluation processes of these models, including key elements like their training code and data. This lack of transparency hinders the broader AI research community's ability to study, replicate, and build upon these advanced LLMs. We've identified several challenges in the current LLM research landscape. Firstly, understanding where the training data comes from and its characteristics is vital for assessing the reliability and biases of LLMs. Without transparency about data sources and composition, it's difficult to identify and mitigate biases that can be perpetuated in model outputs. Also, when training datasets overlap with benchmark datasets, it can lead to misleading performance metrics that don't accurately reflect a model's effectiveness. Secondly, even when data sources are fully disclosed, it can still be hard to reproduce the results reported in studies without access to complete training code, configuration details, and specific datasets. For instance, even though Llama discloses its training data mixtures, it doesn't release its data processing and training code. This means that even models trained using an open reproduction of Llama's data, like Red Pajama, can't fully reproduce its benchmark evaluations, suggesting that additional data processing or training procedures may be necessary. Thirdly, the practice of only releasing final model weights can lead to redundant efforts and unique challenges in conducting certain research. For example, researching the emergent abilities of LLMs or investigating how different training data affects model behavior becomes more difficult without access to intermediate training checkpoints. Researchers often have to either work with the final model, which offers limited insights into its developmental nuances, or start from scratch, leading to unnecessary duplication of work and expenditure of compute. To address these issues, we've developed LLM360, a comprehensive open-source LLM effort. LLM360 models are published with all training and model details, all intermediate model checkpoints saved during training, and full disclosure of the exact pre-training data used. Our contributions include outlining the LLM360 framework, focusing on its design principles and the rationale for fully open-sourcing LLMs. We detailed the components of the framework, including datasets, code and configurations, model checkpoints, and training metrics. We've also pre-trained 2 new LLMs from scratch and released them under the LLM360 framework. Amber is a 7B English LLM pre-trained on 1.3T tokens, and Crystal Coder is a 7B English and Code LLM pre-trained on 1.4T tokens. We discuss the development details, preliminary evaluations, observations, and lessons we learned from Amber and Crystal Coder. We've released all training code, pre-training data, model checkpoints, and evaluation metrics collected during pre-training for both Amber and Crystal Coder. Notably, Amber is released with 360 model checkpoints saved during training, and Crystal Coder with 143. We're committed to fully open-sourcing LLMs by releasing multiple LLMs at various scales. As the first step, we discuss Amber and Crystal Coder, the first open-source LLMs in the LLM360 series. In the future, we plan to release more pre-trained LLMs that are larger in scale, exhibit better performance, and focus on various domains. The rest of this report is organized as follows. We discuss related works and the predecessors that inspired LLM360. We provide a description of the LLM360 framework and the release artifacts that fall into its purview. We discuss the first 2 LLMs released under LLM360, Amber and Crystal Coder, and preliminary analyses of both. Section Summary. The landscape of large language models, LLMs, has seen a surge in popularity and capabilities, with both proprietary and openly accessible models gaining attention. However, the lack of transparency in training processes and data sources hinders the ability to assess biases and reproduce results. To address these challenges, LLM360 aims to fully open-source LLMs, providing complete training details, intermediate checkpoints, and pre-training data. The framework is exemplified by the release of 2 LLMs, Amber and Crystal Coder, with the commitment to release more models in the future. Section 2 Related Work. The section we're discussing is about related work and the LLM360 framework. The project most similar to ours, LLM360, is Pythia. Like us, Pythia also focuses on complete reproducibility of large language models, LLMs. Pythia has provided 154 checkpoints for models ranging in size from 70 million to 12 billion parameters. This was done to support research on how LLMs scale and learn. However, Pythia is a bit outdated now and doesn't reflect many recent practices in LLMs, like training on datasets with over 1 trillion tokens or training on language and code at different stages. In contrast, our project, LLM360, has a release framework that prioritizes transparency and reproducibility. This allows us to keep releasing up-to-date models. Our 7 billion parameter model, Amber, even outperforms the 12 billion parameter model from Pythia in public benchmarks. We're aiming to continue and expand on the transparency and reproducibility that Pythia started in the world of LLMs. Open-source LLMs vary greatly in terms of transparency and reproducibility when it comes to their release artifacts. Some recent LLMs only release their final model architecture and weights, keeping their data sources and most training details a secret. Some are trained on publicly available datasets, while others disclose their data mixtures but don't make the data ready for public training. However, there are a few LLMs that have been released with much more transparency. For example, Eleuther AI models like GPT-J and GPT-Neox included training code, datasets, and up to 150 intermediate model checkpoints. The value of the open-source GPT-Neox training code was shown by its use in subsequent LLM pre-training by others in the community. Insight, MPT, and OpenLLAMA were released with training code and training dataset, with Red Pajama also releasing 10 intermediate model checkpoints. We've noticed a trend that more recent and capable LLMs are becoming more closed in their release artifacts. But our goal with LLM360 is to release modern, high-quality models while maintaining a high degree of release transparency. Now, let's talk about the LLM360 framework. This is a framework for releasing LLMs that promotes open-source transparency, reproducibility, data, model provenance, and collaborative research. LLM360 provides guidance and recommendations for release artifacts that are collected during LLM pre-training and then made publicly available to the community. As part of the launch of LLM360, we're also releasing 2 new pre-trained LLMs, which we hope will foster immediate interest and collaboration in the open-source research community. The first is Amber, an English-language LLM with 6.7 billion parameters trained on 1.25 trillion tokens. The second is Crystal Coder, an English and code LLM, also with 6.7 billion parameters, trained on 1.4 trillion tokens. The pre-training dataset is a crucial part of an LLM and greatly affects its capabilities. So, it's important for users and adopters to know about the pre-training data to assess potential behavior issues and biases. For example, recent concerns about benchmark data leakage into LLM pre-training is much easier to study when pre-training datasets are available for exploration. Furthermore, visible pre-training data improves the extensibility of LLMs in later fine-tuning and domain adaptation. Recent work suggests that training on repeated data disproportionately degrades final model performance. Given the breadth of data modern pre-training is performed on, visibility into the original pre-training data is essential for avoiding repeated data in downstream fine-tuning or continued pre-training on specialized domains. LLM360 advocates for the public release of the data LLMs are pre-trained on. When applicable, details about data filtering, processing, and training order should be released as well. Doing so equips the community with better tools to assess the capabilities and risks of LLMs and to reproduce and build upon existing LLMs for future use cases. The code and settings used for training have a significant impact on the performance and quality of LLM training, and are not always publicly disclosed. For example, we observed that a carefully balanced hybrid data model pipeline, 3D, parallelism can outperform the standard FSDP in PyTorch by up to 15% on our NVIDIA A100 clusters. Another example we observed is that it is essential to keep the inverse frequency matrix in rote positional embedding in FP32, which aligns with the observation in Qwen. In LLM360, we open source all our LLM pre-training frameworks, hyperparameters, as well as the configurations. These include the entire training source code, training parameters such as learning rates and batch sizes, and system configurations such as parallelism dimensions. Section Summary. The Pythia project, which aimed at reproducibility of language models, LLMs, provided checkpoints for various model sizes but no longer reflects recent LLM practices. In contrast, LLM360 prioritizes transparency and reproducibility, releasing up-to-date models and surpassing Pythia's benchmarks. While some recent LLMs only release their final model architecture and weights, LLM360 advocates for the release of pre-training datasets and training code to assess behavior issues, biases, and improve extensibility. Additionally, LLM360 open sources training frameworks, hyperparameters, and configurations to enhance performance and quality. Section: Model Checkpoints. In our work, we often save periodic snapshots of our model during the training process. These snapshots, or checkpoints, are not only important for recovering from any issues that might occur during training, but they're also useful for further research. For example, they can help us study different datasets or tweak the model's parameters. They can also help us recreate rare training issues, like sudden spikes in loss or results that don't make sense, NaN results. Recent studies on model simplification and compression have heavily relied on analyzing these checkpoints, particularly the model weights and how they change during training. We publish our models with all the checkpoints saved during their training, including the model weights and the state of the optimizer, for example, the moving averages used in the Atom optimizer. These checkpoints allow us to pick up training from various points, without having to start from scratch. This makes it easier to study and recreate a wider variety of effects during training. Training our models can take weeks to months, and the patterns that emerge over this period can provide valuable insights. However, detailed logs and intermediate metrics are currently only available to the groups involved in the initial training, which limits our ability to fully understand these models. These statistics often contain key insights that can't be derived in any other way. Even a simple analysis of these metrics, like calculating their variance or norms, can reveal significant findings. For example, the team behind the GLM model proposed an effective algorithm for handling loss spikes and NaN losses by analyzing the behavior of the gradient norm. Our goal with LLM360 is to solve this problem by making all the logs and metrics we collect completely open source. This includes system statistics, like GPU workload, training logs, like loss and gradient norm, and evaluation metrics, like perplexity and downstream tasks. We provide easy access to these figures by sharing them directly on the LLM360 weights and biases page. Some example metrics include downstream evaluation results, training loss, gradient norm, and more. We also explain how to use these metrics and provide an example experiment that tracks the memorization behavior of a model throughout training. We release these metrics in coordination with the data chunks and checkpoints, so researchers can easily find their correspondence. We also provide open access to the code used for analysis and evaluation to promote reproducibility. All the code and metrics can be found in the LLM360 repository. Next, we introduce Amber, the first model in the LLM360 family, as well as the fine-tuned models Amber Chat and Amber Safe. We'll go over the details of our pre-training dataset, including data preprocessing, format, data mixing ratios, and the architectural details of our model and specific pre-training parameters. Our data preparation process is similar to OpenLLAMA. Our pre-training data is a mix of refined web, StarCoder, and Red Pajama v1. Unlike OpenLLAMA v2, we include C4 in our dataset, as we don't want to introduce duplicate documents after the deduplication process conducted by refined web. We combine all these datasets, without any further cleaning, filtering, or subsampling, shuffle them, and divide them evenly into 360 data chunks. In total, we have 1.26 trillion tokens. We use the same model architecture as Llama 7B. The architectural details are directly fetched from the original source. We incorporate rotary positional embeddings, ROP, at each layer of the network. We follow the pre-training parameters from Llama as closely as possible. Amber is trained using the Atom W optimizer with the following parameters. Beta 1 is 0.9 and Beta 2 is 0.95. The initial learning rate is set to 0.0003. following a cosine learning rate schedule that decreases to a final rate of 0.00003. We apply a weight decay of 0.1 and use gradient clipping at 1.0. The model is warmed up over 2,000 steps. Unlike the Llama setup, based on our hardware setting with 224 GPUs, we use a pre-training batch size of 2,240, 224 times 10, instead of 2,048. Finally, Amber is trained on an in-house GPU cluster. Section Summary. During LLM training, model checkpoints are periodically saved to enable recovery from faults and facilitate post-training research. Access to detailed logs and metrics for LLMs is currently limited, hindering comprehensive study. LLM360 aims to address this by open sourcing logs, metrics, and evaluation code, providing easy access to figures and facilitating a deeper understanding of the training process. The first model in the LLM360 family, Amber, is trained using specific pre-training hyperparameters and architectural configurations on an in-house GPU cluster. Section: The GPU cluster. Our GPU cluster is made up of 56 DGX A100 nodes, each one equipped with 480 GB A100 GPS. These GPUs are connected with 4 NVLink links. The cross-node connection is set at 2-port 200 gigabits, sec, 4x HDR, InfiniBand. With our distributed training framework, we're able to achieve a throughput of about 582.4K tokens per second. We use a pre-training framework called LLM 5, which is based on PyTorch Lightning. During pre-training, we use mixed precision with BF16 for activations and gradients, and FP32 for model weights. We've also released a few fine-tuned versions of Amber, including Amber Chat and Amber Safe. Amber Chat is trained similarly to Wizard LM. We use Fast Chat to fine-tune the model for 3 epochs on 8A100s, 80G, distributed by FSDP. The learning rate is set at 2 × 10⁻⁻⁵, with 16 gradient accumulation steps and a warm-up ratio of 0.04. We also fine-tune an aligned version of the model, Amber Safe, using direct parameter optimization, DPO. Amber Safe is trained on a base model that is checkpoint 355, not the last checkpoint, and further optimized on the Safe RLHF dataset. We set beta to 0.1, gradient accumulation steps to 4, and the learning rate to 5 × 10⁻⁻7. We evaluate our models using 4 benchmark datasets from the Open LLM leaderboard. These datasets allow us to evaluate different aspects of our models. We run the evaluation on all 360 checkpoints to observe the model's ability throughout the pre-training process. We've noticed that the HELA SWAG and ARC evaluation scores increase during pre-training, while the Truthful QA score seems to decrease. The MMLU score initially decreases but then starts to increase. When comparing Amber's final performance to other models trained around the same time, we find that Amber is competitive in scores such as MMLU, but lags behind in ARC. Our fine-tuned Amber models perform well compared to similar models. We've noticed that Amber Chat, trained on Share GPT 90K, performs much better than our base model, which is a trend that differs from other models. During Amber's pre-training, we encountered several issues. We experienced NAND loss in 4 out of 360 data chunks. When this happened, we skipped the entire data chunk. We initially planned to train on these chunks later, but they consistently caused NAND loss. We completed our training by using the first 4 chunks from the training sequence. We also didn't save the optimizer states during pre-training, only the model checkpoints. This oversight might have caused the NAND loss issue. Each time we resumed pre-training from a checkpoint, the optimizer state in the AtomW optimizer was reinitialized, which could have affected model stability. In the initial phase of pre-training, our codebase had an issue where model checkpoints were saved with BF16 precision, despite our mixed precision training process maintaining model weights at FP32. We later fixed this issue, ensuring that all subsequent model checkpoints were saved with FP32 precision. The initial BF16 model checkpoints may have caused some accuracy drop in the model. Finally, we'll briefly discuss Crystal Coder. This section provides an overview of the dataset and the model architecture used in Crystal Coder. For a detailed evaluation of results on benchmarks and a comparison with previous works on specific benchmarks, we'll refer you to our future reports. Section Summary. The GPU cluster used in the study consisted of 56 DGX-A100 nodes, each equipped with 4 GPUs and connected with 4 links NVLink. The throughput achieved with the distributed training framework was around 582.4K tokens per second. The pre-training framework used mixed precision with BF16 for activations and gradients, and FP32 for model weights. Fine-tuned versions of the model, namely AmberChat and AmberSafe, were also released. The evaluation of the model on benchmark datasets showed varying performance across different aspects, with HELA-SWAG and ARC scores increasing during pre-training, while the truthful QA score decreased. The final model performance of Amber was compared to other models, showing competitive performance in some areas but lagging behind in ARC. Several issues were encountered during pre-training, including NAND loss on some data chunks, missing optimizer states, and discrepancies in the precision of checkpoints. The Crystal Coder dataset and model architecture were also briefly mentioned. Section 3-Stage Pre-Training Dataset. The dataset used for pre-training in Crystal Coder is a combination of Slim Pajama and Star Coder data, totaling around 1382 billion tokens. Unlike previous methods such as Code Llama, which trained strictly on English and coding data in sequence, we take a more gradual approach. We blend and train on both types of data to strike a balance between coding and general abilities. The training process is split into 3 stages. In the first stage, we train on half of the Slim Pajama data, which is about 345 billion tokens. In the second stage, we use the remaining half of the Slim Pajama data and 2 rounds of Star Coder data, totaling approximately 927 billion tokens. In the final stage, we train on Python and web-related data, including HTML, JavaScript, and CSS subsets from Star Coder, which amounts to 100 billion tokens. We also sample 10 billion tokens from the Slim Pajama dataset in this stage. The preprocessed data and data mixing scripts are available in the Hugging Face and GitHub repository of LLM360. The model architecture of Crystal Coder is similar to Llama 7b, with the addition of Maximal Update Parameterization, MUP. We've made a few minor changes, such as applying rope to the first 25% of hidden dimensions, similar to GPT-NEOX, and using a sequence length of 2048 with an embedding dimension of 32,032. We also use layer norm instead of RMS norm because the CG1 architecture supports efficient computation for vanilla layer norm. Crystal Coder is trained on the Cerebra's Condor Galaxy 1, CG1, A4 exaflops, 54 million core, 64-node cloud AI supercomputer. We also test this model on the 4 benchmark datasets in the Open LLM leaderboard, similar to Amber, as well as coding benchmark datasets, including Human Eval Pass at 1 and MBPP Pass at 1. The results are shown in Figure 4.3. Previous studies, like Pythia, have shown that analyzing the intermediate checkpoints of a model can provide valuable insights. We hope LLM360 can also provide useful resources for both reference and research purposes. To this end, we released the initial version of the project, which includes repositories that analyze the model behavior on various aspects, including model characteristics and downstream evaluation results. We also conduct an initial study on memorization in LLMs. Recent work shows that LLMs may memorize a significant part of their training data, which can be extracted with appropriate prompting. This memorization not only raises privacy concerns but also affects the performance of LLMs if the training data contains unintended duplicates or peculiarities. We use a memorization score to measure the accuracy of tokens in the continuation of length L with a prompt of length K. A sequence is considered memorized or K-extractable if it has a memorization score of 1. We conduct our experiments with K equals L equals 32. We sampled 1,000 sequences from each of the 360 data chunks, and used the first 64 tokens of each sequence to conduct the experiments. Our results show that more than 1% of the sequences are 32 extractable from Amber, and Amber can memorize more sequences as training progresses. The spike at score equals 1 indicates that Amber can memorize a much larger number of tokens than our preset threshold 32. We also find that Amber checkpoints memorize the latest seen data much more than previous data. For each data chunk, the memorization score drops a bit with additional training, but keeps increasing afterwards. We also observe a strong correlation between the checkpoints in terms of memorization score or K extractability. Section Summary. The pre-training dataset used in Crystal Coder combines Slim Pajama and Star Coder data, totaling around 1382B tokens, and is trained in 3 stages. Crystal Coder employs a model architecture similar to Llama 7B, with slight modifications, and is trained on the Cerebra's Condor Galaxy 1, CG1, supercomputer. The model is benchmarked on various datasets, and an analysis of memorization in LLMs is conducted using intermediate checkpoints. Section 5. Summary and take-home messages. In this section, we'll recap our findings and key takeaways from our initial work with Amber and Crystal Coder, part of our LLM360 series. We recognize that pre-training is a resource-intensive process that may not be feasible for smaller organizations or academic labs. Our hope is that LLM360 can offer a comprehensive understanding of what happens during LLM pre-training, such as the behavior of loss curves and the emergence of evaluation metrics, without the need for users to undertake the process themselves. We'll also highlight some potential applications of LLM360 for researchers and developers. Here are some key lessons we've learned from our initial model training. During Amber's pre-training, we occasionally encountered NaN losses, which could be due to random states, training precision, or data quality. Possible solutions include changing the random seed or avoiding certain data chunks. We found that some problematic data chunks can cause NaN loss no matter when they are trained. In the pre-training of Crystal Coder and subsequent LLM pre-training, we found that a well-tuned combination of data, tensor model, and pipeline parallelism strategies, also known as 3D parallelism, resulted in better system throughput than FSDP, particularly in distributed clusters with limited intra-node bandwidth. Data cleaning and quality filtering, along with data mixing ratios, are vital for LLM pre-training. Despite our efforts to closely follow the hyperparameters used in Llama during Amber's pre-training, our performance still fell short. We believe this could be due to the lack of a detailed description of Llama's exact pre-training dataset. Our carefully curated Crystal Coder pre-training dataset, which combines English and coding data, performed competitively with Llama on both the OpenLLM leaderboard and code evaluation benchmarks. We, along with the broader LLM open source community, are actively exploring the best methods for data cleaning, quality filtering, and determining optimal data mixing ratios. LLM360 has several potential use cases. It can be used to conduct experimental studies at any stage of model training. For instance, it's nearly impossible to validate a specific data mixing ratio by conducting full LLM pre-training. A more practical approach is to adjust the data mixing ratios on the fly, such as increasing the data weight in Wikipedia. For building domain-specific LLMs, like those for medical, finance, law, etc., one might not want to start from the last pre-trained LLM checkpoint. Instead, one can choose one of the LLM360 checkpoints, for example, from 50% of the pre-training stage, and continue the pre-training to obtain a domain-specific LLM. Many frameworks for efficient training require partially trained model weights. LLM360 provides ideal model initializations for these methods. Given the broad applicability and high performance of LLMs, applications powered by them can significantly impact various aspects of life. Therefore, it's crucial for everyone involved in the production of LLMs to carefully manage the potential impact and risks. We believe the transparency of the LLM360 initiative can help stakeholders understand these risks. For example, many risks associated with LLMs are related to biases, such as the risk of social stereotypes, discrimination, and exclusion, and the risk of underrepresenting certain languages or domains. By examining the exact training data and bias analysis in Analysis 360, stakeholders can thoroughly review these risks before deploying the models. LLM360 can also assist with risk mitigation by sharing reproducible traces and exact data during LLM training, providing a reusable environment for researchers to design better safeguards against potential risks. We understand the importance of managing the risk of LLMs and are committed to further developing the LLM360 framework to promote responsible usage of LLMs. We invite the community to collaborate with us, either by sharing research results or simply providing feedback.